In the last class, I told you about the heat of the solution. HEAT, heat of solution. Heat of solution. So what is heat of solution? So heat of solution means what you should do is again we are working with the 1 mole. So if you are working with the 1 mole NaOH, so take NaOH. So 1 mole. So how much is 1 mole NaOH? Na is, if you look there, it's how much is NaOH? It's can you look the periodic table? Yeah, so look the periodic table. So definitely O is, I think Na is 23, O is 16, and H is 1. So if you add those all, you get 40. Yes? So 40 gram, take 40 gram, go to the balance, take the bottle of NaOH, take 40 gram. Yes? And take water here. Take water here, I don't know, maybe how much water you want to take. Maybe 100 gram water here. 100 gram water. Everybody see that? 100 gram water. And put a thermometer here. Put a thermometer here and record the initial temperature. So maybe that initial, I have the equation Q is equals to MC T2 minus the T1. That's our equation from the previous chapter. Yeah. So I'm calculating the molar heat of solution here. So you did, probably you already did in the laboratory or you will be doing in the laboratory. Now look here. So the initial temperature maybe is showing the 25 degrees centigrade. So you need to put those number there. So let's put this number here. So M how much? So you have 100 and then 40. So total mass you might have 140. So that's 100. That's 40. 140. And the C is what? C is for the water. That's a 4.2 joule per degree centigrade. That's a constant. That's a mass. And the T2 minus the T1. So throw this 40 gram here and over it, and the temperature will rise to, let's say, 40 degrees centigrade or maybe 50 degrees centigrade. I don't know. 50 degrees centigrade. Now you put 50 there and then you put 25 here and put this number in calculator. Whatever number you get, that is called the heat of the solution. Have you got that? Molar heat of the solution. Clear? So I'm working with the NaOH. You could do with anything. You could do with NaCl, MgOH2, calcium carbonate, calcium hydroxide. You can do anything. Have you got that? This is called the heat of the solution. Yeah. So I'm making the solution and the heat may be released. If heat is released, the temperature rises from 25 to 50. If heat is absorbed here, if initial was 25, maybe it goes down to 15. So if the temperature goes up, you should say exothermic. If the temperature goes down, you should say endothermic. Ever see that? Yes? It's pretty easy, yes? So now let's look another here. So I have the next one is what I have here. All right, factors affecting the solubility. So you already know these things from in your home. So for example, you have a water here. You have water here. Put a little bit sodium chloride here. So if you put a this is water. Now this is sodium chloride. This is water. You see that? So if there is a OH like that, it's a large plus. This is large plus. O is a large minus. You got that? Yes? When you see OH or NH or HF, large plus and large minus. And if you look at the NaCl, this is plus, this is minus. They are like. You see that? So one guy also has plus and minus. Another guy also has plus and minus. So they are called the like things. Yes? Polar. You got that? So polar get dissolved in polar. Like dissolve like principle. Yes? Polar. So what I said there is, so H2O is polar. So look here. H2O, large plus. That's a large plus, large minus in H2O. And NaCl is a large plus, large minus. This is the ionic compound, right? So this guy, definitely these two guys dissolve each other. Like dissolve like, polar dissolve in polar. So this is polar, this is polar. Everybody there? So now let's look here. That's a water. Can I dissolve this guy with this one or not? Let's look here. Look here, this is non-polar guy because C all around C are HHS, same guys, right? So that kind of condition is non-polar. Yes? So this is non-polar, this is polar. If you try to mix this guy with this guy, that does not dissolve. So if you mix this guy and this guy, So you will see water here. This is water, and this is that methane or whatever kind of the compound you have, two layers. So that means it doesn't dissolve. Unlike thing does not dissolve. If polar dissolve in polar, non-polar dissolve in non-polar, but polar and non-polar don't dissolve each other. Everybody got that? Now I can make another here. So let's write something here. So let's say this guy. Is this polar or non-polar? Non-polar. All this is non-polar. And then if I get another guy here, this is also non-polar. Look here. So this is non-polar. This is also non-polar. So if I put this guy and this guy together and shake a little bit, so this is one layer, this is another layer I'm mixing, and I just shake it, and there is no two layer, only one layer. You see that? Dissolve means you don't see the two layer. You see only one thing there. Yes? Ever see that? So if the compound is a plus minus thing or not, so if one compound has plus minus thing, another compound also has a plus minus thing, they should be dissolving each other. But if one compound has a plus minus thing, another compound doesn't have a plus minus thing, they don't mix. Everybody got that? Good. All right, now temperature. So what happened with the temperature? So this is very important. Now let's look at temperature. Temperature. What is the effect of temperature? So you already know this kind of thing, yeah? So let's say this is water here. Now you throw a lot of calcium carbonate here, calcium carbonate, and you see like that. You see a lot of solid. If you want to dissolve it, what should you do? Heat it. Yes? When you heat it, put in the oven and all is gone and you will see all liquid there. Ever see that? If you heat it, things just get dissolved from solid and go to the liquid. Yes? So we always do that kind of experiment in lab. If something doesn't dissolve, I just put in the oven and it heats and everything is done. Ever see that? Good. All right. Now let's look at the last one. So heat. So heat or the increase the temperature you heat it. Yes. Now the third one is pressure. This is only for the gas. Coca-Cola. So if you want to make a Coca-Cola in home, what you should do is like this. So take the bottle here and fill your Coca-Cola water and sugar here. This is water and sugar. It's still not a Coca-Cola. Water plus sugar is here. It's just a sugar water drink. Now if you want to make the Coca-Cola, what you should do is you should take a carbon dioxide bottle from the company with high pressure, and then you need to just connect this here, and then under very high pressure it dissolves here, and then cap it and then take it out and sell in the market. That's how the Coca-Cola is made. Make sense? You cannot make in home because you cannot create a carbon dioxide pressure yourself. Yeah. So you need to buy the carbon dioxide, a lot of carbon dioxide here, and then when you connect this one there, the carbon dioxide gas dissolve here and become the sour in case. Ever see that? So you need to press with a lot of air, carbon dioxide inside that bottle, and carbon dioxide gets dissolved. Now you bring it in the market and open it. What happens is that you open the Coke bottle? The gas comes out. Why gas comes out? Because the pressure here outside is very low pressure. You see that? So this gas comes out and go out. Ever see that? So why previously dissolved? Because I was connecting here, a lot of pressure here. So I connected here, therefore the gas dissolved here. Now I do that one and I cap it and sell in the market. But when somebody open this one, so there is not much pressure, a little bit air there, so that cannot press down there. So whatever already dissolved, get out, and you see the fizzy thing coming out. Ever see that? So in future, that's called the Henry's law of solubility. So you don't have to worry about. So if you give more pressure, a lot of gas we can dissolve. Does that make sense? So in the low pressure carbon dioxide. So for example, I am breathing out. If I try to do my Coke, I don't have enough carbon dioxide there because I cannot give that much pressure. I can give out a pressure, right? Carbon dioxide, but the carbon dioxide coming out from my mouth doesn't have that much pressure. So I cannot dissolve carbon dioxide in water that much by just blowing. I need to get a carbon dioxide gas bottle and I need to connect that with the Coke bottle and then open the carbon dioxide bottle and that gas goes and dissolve in that water. Ever got that? Yes? It's important, yeah? The solubility, so solubility depends on Three factor. One is like dissolve like, similar people are mixing each other. Number two, you need to heat to make it, if something is not dissolving, you need to put in oven and heat it and things dissolve. And in third, if you want to dissolve gas in water, you need to connect with a big heavy tank of gas with the water. Yes? Everybody got that? All right, so let's go to the next one. This is a like dissolve like. Look here. So these guys, so if you look there, these guys are all CC. You see that? C, 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 C. These are non-polar. Non-polar. This CF are non-polar. So this guy doesn't dissolve in water. Vitamin A. So do you take vitamin supplement in home or no? I take vitamin C, vitamin A, sometimes vitamin D. You see that? So this is a vitamin A. So it doesn't dissolve in water. So if you put a vitamin A in water, it does not dissolve. But tiny polarity, you see that OH is a polarity here. That's O is a big minus, H is a big plus, but they have a big non-polar. So this guy doesn't dissolve in water. Now, what I'm saying here is like this. So, so there are a lot of C. So C, 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 so this kind of thing. So this one I didn't draw. You see that? I just draw that line. This one. Ever see that? In organic chemistry, we draw just the line. We don't draw like that. And at the end, you see OH here. So this guy has a minus, big minus. This guy has a big plus. But this guy is a no plus, no minus. No plus, no minus. So this is called hydrophobic part. Hydrophobic. So it doesn't dissolve in water. Not dissolving is too big, dissolving is too small. So as a whole, it doesn't dissolve in water. Ever see that? But this is a vitamin C. Look at how many over there. This is a minus, this is a plus, this is minus, this is 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 plus. A lot of plus minus. So vitamin C dissolve in water. Ever see that? Because water also plus minus. Look here, FOF. So water is also plus and minus, and vitamin C has too many OH group, meaning too many plus minus there. So that's like the vitamin C is like the water. Yes. So if you put the vitamin C in water, it's going to dissolve. Everyone got that? Yes or no? All right. Now let's go here. That's a Coke thing I already told. It's a Coke is dissolved under very high pressure. So Coca-Cola company produce a lot of carbon dioxide and put in sugar water. And then carbon dioxide dissolves and it becomes sour in taste. So Coke is tasty in drink, right? But we cannot make it in home because we don't have a carbon dioxide tank in home. But when we open this one, all gas comes out. Why gas comes out? Most of the gas come out. Why gas comes out? Because pressure here is low. Because the pressure here is low, low air pressure there. Everyone got that? Good. Have you understand this one? Yes? All right, good. Now let's go next. Now, measuring concentration. So, solution could be saturated, unsaturated, or supersaturated. Is there a super? Yes. So, solution are three types: saturated, unsaturated, uh, supersaturated, and saturated. It's very important, yeah. So look at, so this is water. You have water here. You put salt. You put salt. It's a salt solution now. Salt solution. Salt solution. There is no solid here. No solid. You cannot see solid here. You see that? No solid here. Now you put a little bit salt and that also dissolves. So this is unsaturated. So if the solution can dissolve more solid added, then that is unsaturated. You see that? So you guys are unsaturated now. I am saturated. I already made money and I also in my life. So I'm kind of unsaturated. I'm not looking anything. So you are looking education, you are looking future needs. So you are kind of unsaturated now. Ever see that? Just like this. So unsaturated. For example, this is the solution. There is already salt. You are putting more salt and salt is dissolving. So that's a unsaturated. Yes? Now what is saturated then? Now look here. So you have solution here, salt solution. This is salt solution in water. Now put a little bit salt here. So that salt, that added salt, go and sit here like the solid. So that solution was already saturated. He doesn't want to take anything else. Ever see that? Yes or no? Saturated. He was already saturated, therefore he could not dissolve the solid. Yes? Now supersaturated. It's interesting. Now let's talk about the supersaturated. So what is supersaturated? Somebody, any question?
It's when a
Exactly, supersaturated. Yes. So supersaturated. So let's look here. So this is a solution, salt solution, salt solution. So let's say the temperature of this. Put thermometer here, and it's a saturated condition. Let's say 40 degrees centigrade. 40 degrees centigrade. You see that? Now what happens if I put this in freeze? It's a saturated. If you put anything, it cannot dissolve. Now put in freeze. What happens if you put in freeze? It becomes cold, right? So the temperature decreases. So that's a saturated solution at 40 degrees centigrade. If I put in the freeze and temperature becomes 25, it will throw some of the solid out, and that goes and remain as a solid. So that condition is called the supersaturated. So saturated solution at higher temperature uh, throws out the solid to the bottom at lower temperature. Ever see that? So supersaturated. Sometimes you can do something like this. So if you take the filter in organic chemistry class, so let's say this is a supersaturated solution. This is supersaturated solution. Supersaturated solution. There is no solid here. Yes, there is no solid. Put a tiny bit speck of the solid. Tiny bit. Yes. Put tiny bit. This speck here, a tiny bit here, and you will see a lot of coming down here. Interesting. Why that happens? Nobody knows. You see that? So, for example, we have a 20 students here. I put one student from here, then come try to sit here, but all 19, 20 students go out from here. Ever see that? So that's a supersaturated condition. So how do I know supersaturated condition? So what I do is, I just do a couple of things. So to identify the supersaturated, I can do that. So let's say I have this solution. I want to test if it is a supersaturated or not. So I take a glass rod and scratch here. So I just do like this, scratch. So on scratching, you see a lot of solid from here just settle down. So that was already supersaturated. Ever see that? Or what I could do is, I have the supersaturated solution there. I put a small speck, so maybe one tiny a piece of the salt there, and I see a lot of salt settling down at the bottom. Why does that? Why does it do that? I don't know. Nobody knows. Ever see that? So it just throws more. So there was a, you think you are not seeing any solid, you try to put a little bit solid, and a lot of solid comes and go down at the bottom. Yes? So that was a supersaturated. Ever know that? Yes? Or no? Yeah, good. So, all right. So what is the solubility? So look here, the solubility. So solubility is like this one. So take the 100 gram water, 100 gram water, and put salt to make saturated solution. How much? Maybe if you put 30 gram water and 30 gram salt in 100 gram water, and this becomes saturated. This is saturated. So then this solution is called solubility. You see that? What is the solubility of salt here? I have a water here. I take 100 gram solvent, 100 solvent in water. And how much I put here? 30 gram salt. And what happened here? Solution becomes the saturated. So that 30 is called the solubility. Everybody got that? Yes or no? So 30 gram per 100 gram. Now look here, what I was telling about the supersaturated solution. Look here, this is a supersaturated solution. And put a tiny crystal from outside, you see a lot of coming down, settling down there is a crystal. Ever see that? So this is supersaturated. Yes? So this solution is supersaturated or not. I am just trying to see supersaturated or not. So I put a tiny piece of the crystal here into here, and I get a lot of crystal coming down like that. It's just like if this class is supersaturated, oh, see that Casey come out, so everybody will go out, just like that. So that's a supersaturated. Yes? Does that make sense? So that's how they make the crystallization, sugar crystallization, or pure organic compound crystallization. That's how they crystallize the sugar. You see the sugar we eat every day? So you see the nice looking crystal of the sugar or the salt, they always make it like that way. So what they do is they take water here and they dump a lot of sugar there at the beginning, and then they heat it, maybe 50 degrees centigrade. When this is heated at 50 degrees centigrade, and then suddenly cool to 25 degrees centigrade, and then you will see crystal, nice looking crystal like this. Have you got that? How to make the sugar now or the salt? Nice crystal looking, very beautiful. That's how we do. Yeah. So we need to take a lot of the raw material. What kind of the raw sugar you collect from the farmers, right? And then you need to put in water, and then you need to put a lot of sugar in the water, and then heat and heat and heat, and then all dissolve first, and then start to cool. When you cool it, the crystal will come and sit at the bottom, and then separate them and sell in the market. That's how we do the crystallization. Have you got that? So you will do in the organic chemistry laboratory. You can take the lab next semester. So there was. It looks like there was nothing. It looks like there was nothing, but there was a lot of things. So if you try to put a tiny bit of this one, a lot of that dissolve would come down and sit like that. Have you got that? And then you separate them, filter them, and sell in the market. The crystallization is the way of purifying the material. Yeah. Good. All right. Now look here. So concentration unit. How do we express some concentration unit? So how much is there? So I already told you I put 30 gram of salt in 100 gram of water, right? So this is one way of saying. So 30 gram of 30 gram in 100 gram. So there are multiple way of doing expressing the concentration. So what you could do is, let's say I say how much water I have here, 100 gram, and how much salt I put here, 30 gram. So what is the percentage concentration? So percentage is equals to percent concentration of solution is equal to salt in the top and the bottom 100 and 100 plus 30, and you need to multiply by 100, and this is called percent state. Gram of solute, that's solid, divided by the solution, multiply by the 100. You got it? Yes or no? So how much salt you put? That's you need to put that in the numerator, and denominator salt plus water, and you need to multiply by 100. That's a percentage of the concentration of the solution. Make sense? So I put this question in exam. A lot of students last year did not put this 30. They just put 100. So that's wrong. Only half I gave them. Yes? You got that? So you need to put both number here, and then 30 salt, and then 130, and then you multiply by 100. Yes? Yes or no? Got it?
So whatever you're trying to find divided by the total.
Yeah, total. Whatever is the total here. Yes? So they were doing, so let's say I put something like this. So I put a 50 gram water here, and then 2 gram salt here. What is the percent solution? So percent would be 2 divided by 50 plus 2 multiplied by the 100. And put in the calculator, you get that. Make sense? Don't ask me why. They did this way, and that's why we need to do that way. Yes? Got it? Alright. Now percent by volume. So what is the percent by volume? Let's look the percent by volume. So maybe there are some problem here. Let's go and look the percent. Look here. So I already did there. Total mass of the solution. 10 plus 50 of 10, and then you put in the calculator, you get that. You got that? So I don't have to make a new problem. Now percent by volume. So let's look here. So to prepare a solution, we dissolve 205 ml of ethanol to sufficient water to give the total volume of 235. So let's look there. So this is the graduated cylinder, and they say we dissolve 205. So this is a 200. This is a 200 mark. Maybe this is a 500 mark here. So we did. We have 205. So maybe 205. So this is ethanol here. You see that? 205. You see that? So I put that much ethanol, right? Now I put how much I added water, and how much I got there? 235. So I added water here. I added water, and I reached to 235 here. 235. So look here. You see that? Yes? So 205 was my ethanol, and then total is 235. Then multiply by 100. Look here, 205 was the ethanol. This part I put there first, and then I added some water to make it 235. I didn't add 235. I add 30 to make 35. Yes? Have you got that or no? Yeah. So I was already up to 205. I was already 205. That was the ethanol, and I added 30 ml here from this to here. So that becomes 235. So 205 divided by 235 multiplied by, always at the bottom you need to put whole. Yes, whole thing. That's a whole thing. Whole thing goes to the bottom. Previous also whole thing goes to the bottom, right? Everybody there? Good. Whole thing. Just don't put only 205. You need to put everything. Yes, at the bottom, and then you multiply by 100. Good. Now let's go next. Mass or volume. Mass divide by volume. So here mass divide by volume. So let's say here you have, so if let's say 3 gram of salt is dissolved in 250 solution, so I have this guy here, and then I have here water. So I have water. How much water I have? I don't know. How much water I have? I don't know. I put the 3 gram salt here. So this is 3 gram salt. Salt at the beginning. You see that? How much salt I put here? 3 gram, right? Yes? I go to the balance, get the 3 gram and I put it here. And I put a little bit water and shake it and I dissolve it. Then I dump water up to here so that this whole thing becomes 205. 250. 250 ml. You got that? Now percent solution. Now the formula is mass divided by volume. What is the mass I have? Salt. So mass is 3 gram and the volume total is 250, and then you have to multiply by 100. That's how also they express the percent mass by volume. Yes? So how much mass you have? Divide by total volume and multiply by 100. Yes? Good. Alright, now let's go there. So you put that number in. Now parts per million. Now if you work in future in the environmental industry, you will be working with the parts per million. If not, probably you never do that kind of thing. Yeah? In environmental industry, we do it in a part per million. What is million means? Who want to try? What is the 1 million? 10 to the power 6. 10 to the power 6 is called million. Ever see that? So let's look here. So let's say parts per billion. So mass of the solid divided by the mass of the solution. Let's say here you have a 0.00005 gram of salt in let's say 6 liter of solution. Ever see that? So this is the problem. So you go there in the ocean and collect 6 liter water. Yes? And in that 6 liter water you found that much salt. Yes? So what is the part per million? You got that? So it's a tiny number is there, right? So in that case, the salt 0.0005 divided by 6 liter. 6 liter would be approximately 6 kilogram of water and multiply by 10 to the power 6. Put this number in water calculator and calculator gives the number. 6 liter is 6 kilogram. You see that? 6 liter. Sorry, yeah, this is a gram. So this is a gram. Liter would be kilogram. So I would multiply by 1000 to be gram in gram. Like this. You got that? So you need to have the same unit up and down. Yes? So 1 liter is 1 kilogram. Yes? So if I have the numerator gram, denominator must be gram, so I put another 1000 there. Yes? Does that make sense? So it's just like that. Now if the solution is even weaker, so what you would do is, so maybe the solution is like this, 0.00005 gram in, let's say, 1 kilogram water. Maybe one, I don't write the kilogram now. That's a 1000 gram water salt. Let's find in part per billion. So look here how small amount of salt is there, right? In that amount of water. So we need to do the billion in part per billion. Part per billion is 10 to the power minus 9. So for part per billion, salt divided by solution mass multiplied by 10 to the power 9. Salt how much? 0.123456789. So 0.2345678 divided by 1000, and then you multiply that by 10 to the power 9. So when the salt is very tiny amount in water, we need to do either part per million or part per billion. You got it? Yes or no? Very simple. So you might say, why I didn't get this number and this number put here? So if I add 1000 gram with this one, I will get 1000.0000000005, which is the same thing. That doesn't make any difference. You can try doing it, it will not make any difference. Make sense? When salt is very, very small, adding with that 100, 1000 plus 0.0000, whatever is the 1000. You got it? So we don't have to do that. If this number is really, really small, the adding doesn't do anything different. Yes? All right, like that. Good. So let's go here. Acid base titration. So this is very important. Acid base titration. What do we do here? Is like this. Acid base titration. Now, look here. So this is a you take burette here. So this guy's name is what? Burette. Burette. And there is a button here. You can just rotate it a little bit and it opens and give the solution down. So this is called burette. B-U-R-E-T-T-E. Burette. Burette. So here it's a mark like this. So 50, 25, 10, 5, 0. This is label like this. 0 milliliter, 5 milliliter, 10 milliliter, 25, 50 milliliter. Everybody see that? Yes or no? Good. This is burette. In burette, I am putting sodium hydroxide. Sodium hydroxide solution. Sodium hydroxide solution. So NaOH in water. Yes? You got it? Yes? Alright. Now this is called Erlenmeyer flask. So this is called, in my time, we used to call conical flask. They call Erlenmeyer flask nowadays. Erlenmeyer flask. In this Erlenmeyer flask, this is a base. So if this is a base, you are going to put acid here. Acid here. Some acid. You got that? Acid, maybe HCl, H2SO4, whatever you want to put. And then put 1 drop of phenolphthalein. Phenolphthalein, 1 drop. This is called indicator. So no color here, no color. And no COLOR color. You see that? What did I put here? A little bit hydrochloric acid. I put a drop of phenolphthalein. I didn't see any color here. You see that? Now I put this guy here. I put this guy here, and open this button. You see that? What happens if I open this button? It started to fall down right here. Yes? NaOH comes from here and it goes here. So I just keep putting. At a point, it becomes pink. Suddenly, it becomes a pink color. You got that? Yes? Suddenly becomes the pink color, and I need to just close this one. So how much I put here? Maybe I put 25 here. See that? When I put the 25 here, and suddenly become pink, and I stop that. Ever see that? This process is called titration. So either way, you can do either way. You can put acid here, base here, or base here, acid here. Yes? If there is no pink, pink comes. If there is a pink, pink disappears. That's all it does. So that's why we call indicator. Ever see that? What is the indicator of this room? Clock. So when the clock hits 3:15, I cannot stay here. I should go out. Yes? So indicator is that color giving thing. So don't put more. So you cannot put more. You see that? So that's the indicator. Everyone got that? Yes? When you see the color, you are done. Or if there is no color, color appear and you are done. Yes? So we are not done it for this class. We will be done at 3:15. Yes, so we cannot stay more than 3:15 here. So that's the indicator. Our indicator is the clock for this. Got it? So that's an indicator. That phenolphthalein gives color or no color. That's a indicator, and that's an acid, that's a base, and we are putting acid and base together until either if there is a color disappear, if there is no color appears. Yes, so the reaction is complete. It's just like at 3:15 today we will be done. When the color appears, that reaction is done, and the reaction done means equivalence point. We reach the equivalence point for that reaction. Reaction is just complete. Everybody got that? Yes? All right. So this method is called what? It's a titration. I don't know why they call titration. Yes, but they call this process titration. Acid-base titration. Acid and base. Acid is like a HCl. Base is like a NaOH. And we are mixing NaOH and HCl till if there is no color, color comes. If there is color, color disappears. You got that? Aaron? All right, like that. So what is the equivalence point? When you see the color, the reaction is complete. That's the equivalence point. Yes? or some in point. So in point and equivalent point are very similar. Yeah, don't get confused here. I'm not going to explain too detail. So you already know the what's the meaning of the titration. When we do this kind of the work, we call that is a titration. Yes, good. Now let's go here and look here. So in this one there is a HCl. There is a HCl, hydrochloric acid, and in this burette we have a NaOH, and they have put a little bit of phenolphthalein here. Phenolphthalein, one drop, just to show the color, and there is no color. So you open this one, and a little bit, at a certain point this color comes here. Color come disappear, at a certain point color comes and stays there. So we are done. You got that? This process is called titration. Yeah, so probably you will do in next semester, I don't know. Now let's look here. So I don't want to do this one. So now let's look this one. So acid base titration, there is a one problem. So I want to do this problem. So this is the reaction here. So the acid is HCl. So what they did is HCl is here. See, that's a HCl, they put it here. Acid, HCl. You see that? Yes, HCl, they put that HCl there. How much HCl they put there? 20.1 ml. You got it? 20.8 ml. So they put a little bit acid in this one, and then they 20.8 ml. So they put it here. So that's the volume. So we call V1 is equals to 28.1 ml. How much HCl is there? 28.1 milliliter. You got it? Yes, 28 point. And then they put a tiny bit of phenolphthalein here, one drop. So we don't do one drop phenolphthalein. No color. There is no color. You see that? And then what is the strength of this guy? This guy M1 is 0.2437 molarity. So we have this two number for this HCl. So that's HCl, and the concentration of this guy is 0.2437 molar, and the volume of this guy is 28.1 milliliter. Remember that? How do we measure the volume? From the graduate estimate. Yes? Got it? Yes? Now you need to take the burette. So put the burette here. Burette here, like this. And there is a knob you can just open and close. So there is a NaOH, and there is a mark like this. So there is a 0, and then there is a 50 here, and then this is a 25, maybe this is 40, this is 10, like that. It's marked like that. You see that? Now what you should do is you should open this one. Just open this. Until how long you should open? When this becomes just the pin. You got that? Yeah, done. Yes? So how much you put to get the pin? He's saying 25 ml. So all this 25 is gone, and he put up to here. So look here. So this is gone. So that's gone part. So that's a V2. V2 is 25 ml. And then M2, what is the concentration of this guy? I don't know what is that. I need to calculate that. You see that? Yes or no? Yes? Alright. Now I have the equation. Now look this equation. When hydrochloric acid and barium hydroxide react, there is a 2 and there is a 1 in the balanced reaction. Yes? You see that? The 2. So what I do is a very simple. So if you do the one, 2 HCl is reacting with 1 BaOH2. 1 BaOH2. So don't try to understand too much here. What I do is, so for this guy I was writing M1 and V1. For this guy I was writing M2 and V2. You see that? That's a barium hydroxide. This is HCl. Everybody? Yes or no? So just like the last class, so you can just M1 by M1 V1 by 2 is equals to M2 V2 by 1. So you just put those numbers there and you are done. So M1 V1 by 2, M2 V2 by 1. Yes? So this side M1 V1 by 2. M1 is how much? 0. Look here, M1 is how much? The molarity is 0.2437. So you can write 0.2437 there. 0.2437 there, and then multiply by V1 is a 28.1, and that's a divide by 2, and then V2 M2. What is V2? V2 I got 25 from there. 25 M2 I don't know how much, and I have 1 there. Now you want to get this M2 value from here. So to do that, make alone this side. So 1 goes this way, 25 goes down that way. So you don't have to do this one anything. So 25 go down here like that, and that's the M2. Just put in the calculator and you get the number. Everybody see that? So you know the concentration of the barium hydroxide by doing that. Yes? You got that? So answer is there. Now if this was not an equation, this equation there was a 2, therefore I write 2. So what would you do for the reaction like this one? So your equation for the reaction like this one. Let's say I have the HCl and NaOH, and I'm doing this NaCl and plus H2O. Look here, there is a 1, there is a 1. You see that? Yes? There is no 2. Previously I was writing 2 and 1 here. Therefore I write 2 there. But now your equation becomes, there's a M1 V1, M2 V2, and there is a M1 V1 by 1, M2 V2 by 1. So you don't have to write this 1. 1 doesn't do anything in any way. Yes? By multiplying by 1 or dividing by 1 doesn't do anything? Nothing. So you don't have to do anything like that. So M1 V1 equals to M2 V2. Yes or no? So just put number. You see that? There was a 2 for HCl. There was a no 2, only 1 there. So V1 M1 by 2, V2 M2 by 1. So that's how it works. Yes? So it's just exactly like how I teach the mole divide by mole in chapter 5. Yes, chapter 4 or 5. Everybody see that? So in that time I was telling you, okay, you have a $10, you go to Walmart, and then 3 apple, $5 can buy 3 bag, $15 can buy how many bags? Just like that. Everybody see that? So I was telling you to put this number up and then down, whatever number there, and equate, and you are calculating the number of mole what you would produce, right? So this is how it works. A little bit, you got that? Yes? So how does 2 and 1 come there? Yes? So basically M1 and V1 gives the number of moles. So if you go back and look your note, moles is equals to molarity. Molarity is M. Molarity M is equals to moles divided by the volume in liter. So when this molarity is M, so this molarity is M. So if you take this way, M and V is equals to number of mole. You see that? So MV molarity multiplied by the volume in liter gives you number of moles. Yes? So you need to go back and read the chapter 5. Does that make sense a little bit? Yes? So just practice that, and then so hopefully I will put this one in the exam and see we understood or not. Yeah? So probably I will not put this one. I might put 1 to 1. V1 M1 equals to only V2 M2. You don't have to put 2 or 1. Yes? You got that? Alright, so try this one. So I put that there, so you can just look there, that one. So now colligative property. Oh, all right. So colligative property. How much time I have here? Colligative property. So before going there, now let's do a couple of equations there. So if I told you HCl plus, I'm titrating HCl NaOH, and then I take NaCl and H2. I don't care what is there, and when I balance this reaction, there is 1 and 1. So in this case, what I'm telling is M1 V1 is this guy, M2 V2 is this guy. This is the molarity, this is the volume. This is the molarity, this is the volume. So in this case, you can simply write M1 V1 equals to M2 V2. This is the formula. You got it? Yes or no? There is a 1 and 1. So simple. Yes? Good. Now if I have another equation like this one, let's try write this one. Now I have MgOH2, MgOH2, and I am writing that with the HCl, and then I get the MgCl2, MgCl2 and H2 like that. And then if I balance that one, I need to MgCl2 maybe 2 here, MgCl2 maybe 2 here, 2 here, and everything is good. You see that? Now what will be the equation for this one? So the m1 v1 you write here, and m2 v2 you write there. So m1 v1 by 2 is equals to m2 v2 by 1. The formula becomes this one. You got that? When you balance that one, so if you can do m1 v1 this one too. It's just you are taking, if you are taking the m1 v1 here, this should be m2 v2. Got it? So what I'm saying is, you can write this guy is a m2 v2, this guy is a m1 v1. Either is fine, but this divide by 1, this divide by 1. So that m1, if that's you are taking m1 as acid, v1 is also acid. Yes? If you are taking m1 as base, v1 should be also base. Got it? Same thing. m1 v1 is for the same thing, m2 v2 are for the same thing. Yes? That, and then that one. Now let's look the colligative property. Probably this is the last thing of this chapter, colligative property. Colligative properties of the solution. Properties. What is colligative property? Depend on number, nothing else. So if you are looking at property, it depends only on the number of particles. How many particles are there? But how big is a particle? How tall is a particle? How short is a particle? It doesn't count. You see that? So this class is like a perfect light. So the size of this class was 30, right? This class size is 30. So our class property is like the colligative property. How tall student come here? Which year student come here? Which major student come here? Doesn't depend on the other quality. We are just interested to get 30 student here. Have you got that? So the quality, the property of the solution, it only depends on the number of particles, but not other. You got it? All right. So now let's look here. So what is the colligative property? Or property of the solution that does not depend on anything else. It depends only on the number of the solute particle. Look here, number of the solute particle. So the quality of this class only depends upon the number of students. I don't need to be very bright student. I don't need to be very weak student. I don't need an average student. Whoever comes here, that's all matters. It's just it depends on the number. Ever got that? So if you are looking some property, it only depends on the how many people are there, but not other. How tall they are, how short they are they boys or are they girls? So everybody see that? Yes or no? Yeah, like that. So now let's look at this one. So we have only 4 colligative property. One is osmotic pressure, another is vapor pressure, lowering, another is boiling point elevation, another is freezing point depression. So there are only 4 colligative properties in the world. You see that? Only it depends in the number of particles of the solute and nothing else. Yes? So let's look here what that means. So osmotic pressure. So are we studying the osmotic pressure? Types of the solution? Whatever. Vapor pressure. Okay, so we start from here. So boiling point elevation. Let's start from here. I even did not. I don't know where it's coming from. I will just talk that later. Yeah. So let's start from the not osmotic pressure. Let's start from the. Not the boiling point elevation. So I'm working with the boiling point elevation here. Boiling point elevation here. So what I'm doing here is I have water here. So I have 100 gram water. Can you see that? I have 100 gram water. I'm talking to boiling point elevation, and what does that mean? Yes? 100 gram water. I put a thermometer here. Thermometer. That's a thermometer. Thermometer shows what? Temperature, right? Yes? Now I put this in oven. This is what? Oven. Now I heat. I keep heating and I keep heating and I keep heating. And when the thermometer hits 100 degrees centigrade, it starts to boil. You see that? Yes? When thermometer is in 100 degrees centigrade, water starts to get the bubble fast. That's the boiling. You got it? Yes. Now I put a sodium chloride. in another, exactly I do the same experiment. So what I do here is I take 100 gram water, or you can say that 200 gram, it doesn't matter. But you, whatever you did here, do the same thing here, 100 gram water. Then in the experiment, we always do the identical condition. Yeah, if you did one experiment with 100, you should try to do another experiment with also 100. Yes, if you try to do with one with the 50 gram, try to do this with the same 50 gram. Yeah, so like that, 100 gram water. Now I put a little bit sodium chloride, NaCl, a little bit sodium chloride. Now I put a thermometer here and I put it in a heater, oven. Now previously it was boiling at what temperature? 100. Now it will boil at 150, 105 degrees centigrade. You see that? It only boil at only at 105 degrees centigrade. So the boiling point become what? Higher. So this is called the boiling point elevation. Got it? So salt water always boil at higher temperature than the pure water. That's called the boiling point elevation. Yes? Does it make sense? Yes. All right, like that. Now I put a NaCl here. NaCl. So NaCl. But I could put there, let's say, KCl. Is K and Na same or different? Different, right? So Na is this size, and K is that size. You see that? In one case, I put this guy there and it boiled at 105. Now I put this guy there and it also boiled at 105 degrees centigrade. The size does not matter. How many particles you put, that matters. Ever see that? It's just like this class. I don't care who is coming. Maybe all girls are coming. Maybe all boys are coming. Maybe very bright students are coming. Maybe very weak students are coming. But as long as we have 30, the property of the class or the quality of the class is exactly the same. If you got that? So either I put a 1 gram NaCl or I put the 1 gram KCl, the boiling point elevation will be the same. So the identity does not matter. You see that? Identity means one is a KCl identity, another is NaCl identity. If I put the same number of the particle there in the water, they behave exactly same way. So 105 and 105. Does that make sense? So therefore it is called boiling point elevation is called the colligative property. You got it? So if salt is added in the water, the boiling point of water goes up. So, but if I put the equal number of the particle in all water, the boiling point of all water is same. No matter if I put KCl, NaCl, or NaOH, whatever the number of particles I'm introducing, the number of particles same. You got that? Yes. Good. So we have an equation here. You can easily calculate the there is an equation. We have this equation delta TB. So that's a boiling point elevation is equals to KBM. So look here. So delta TB is previously at what temperature water was boiling? 100. So if there was a pure water and pure water was boiling at 100, right? And now with the salt, how much is it boiling? 105, right? So 105 minus 100 is that delta TB. 105 minus 100 is a delta TB. And look at that. So how much is that? 5? 5. So exactly, that's a 5. 5. Now this is a constant, you don't have to worry about this. People have already measured it and they keep the constant. Maybe this is the 0.02. Now you can identify how much M is there, how much mass of the salt is there. So M is equals to 5 divided by 0.02. So you can find the molality of the solution. Molality is basically it's like a molarity, yeah? But it shows the how much salt is there in 1 kg solvent. That gives. You see that? What is this M? That M means how much salt. M means amount of salt, gram of salt, not gram, mole of salt, moles of salt in 1 kg water, 1 kg water. M, that M. Make sense? So how much salt? So just by looking the measuring the pure water, 100 with the water with the salt, 105. You subtract from there to there, you get 5, and then kb. You just look the book and then get this number for NaCl in water system, and then M. So you can calculate how much salt is there. You see that? Have you got that or no? So you can calculate how much salt is there in water by taking just the boiling point. You see that? So the boiling point difference was 5 degree and then kbm. So this is a constant. You will find that in the books, and then you put that number there. So if this goes down here, and then you can calculate m. How much salt is there in this water? I don't know, and I could calculate just by using that equation. Yes? Makes sense a little bit? So let's look another one. So this is the boiling point elevation. Now I'm going to do the freezing point depression. So we boiled this one. Now let's do this one with the freezing. So this is a freezing point depression. So let's look here. Freezing point depression. So freezing point depression. So let's take ice. So this is ice here. Ice. And you put the thermometer. You see the solid here, solid ice. Thermometer shows 0 degree centigrade. Yes? Yes or no? Yes. So when you have ice and you put the thermometer in the ice, you get the 0 degree centigrade. Yes? Now, in another case, so take the salt water here. So put some salt, NaCl, and this is water, salt water. And then when you put that, if there is a ice, it shows -5 degree centigrade. You see that? So look at salt water. There was a salted water ice there. There was a -5 degree centigrade. There is only water. There was a 0 degree centigrade. So freezing point. What happened to freezing point? Decrease or increase? It was here. It was here 0. Now the temperature dropped down to -5. Freezing point decrease. Make sense? So why do people, the city people, put salt in road during the winter time? To melt it, exactly, to melt it. You see that? So normally it's a 0. So if there's a very, very cold outside, there is a water, and then at 0 degree centigrade, there's all ice in the road. You see that? But if they put the salt, it only becomes solid at -5, but 0, all will be liquid. You see that? Yes? So when you put the salt in the ice, the freezing point depresses. So ice, water does not freeze. Good. So when you put salt in water, water does not freeze easily. You really need to be very, very cold to freeze it. So that is called freezing point depression. Everybody that? So if they don't put the salt in road, all road is covered by ice, right? Yes? But when they throw a lot of salt there, ice doesn't, the water doesn't freeze. It's the water and it just flows and goes out. Make sense? So like that. So freezing point depression. Now you can do the same thing with the equation here. So what you do, how much salt is here? I want to calculate the amount of salt here. Yes? Amount of salt. How much salt is here in this figure? This is a pure water. There is a salted water here. So how much water is salt is there? I want to calculate. Delta TB is equal to KFM. So again, delta TB is, look here, 0 minus 5 is 5. So that's 5. You got that? Yes? 5. Now this KF you get in the book. So 0, maybe 0.02. I don't know how much is that. And then M, how much is salt is here, then you can calculate. So you put this 0.02 down here, 0.02. Now you could calculate M, how much salt is there. Does that make sense? Yes? So the KB and KF you don't have to measure. So people have done a lot of experiment and tabulated those data in the standard book, and you just bring it and look, oh, what is the KF value for NaCl in water? So 0.02, like that. Just Google it. Yes? So how much salt is there in your water? Without measuring, without having balance, with just a thermometer and heater, you could find out how much salt is there in water. Did you get some idea? Yes? Good. Now, I just want to... How much time? Still weak. Why boiling point elevation occurs here? So now let's look here. Why boiling point elevation? So I just want to talk about that cause. Why salt water boil at 105 centigrade, pure water, 100 degrees centigrade. You see that? That's what we have been talking, right? If this is the water here, the water here, put a thermometer and then put in the oven. Heat it. When the thermometer hits the 100 degrees centigrade, you see a lot of bubble coming out. It's boiling and boiling. Yes? Pure water. You got it? But here, you put water here, and then water, and then you put some salt. Salt here, water plus salt. Put the thermometer here. Put on the oven. Now you start to heat. When this hit 105 degrees centigrade, and only this water boils. You got that? Yes or no? Yes? So it's called the boiling point elevation, right? Why is that? So look here. So there is nobody to block this surface. So this is the water and it's pure water. So water can go up, water can go up, water can go up, water can go up, water can go up. Water easily vaporizes and boils there because there is nobody to block. You got that? But here, if you look here, this is the water and salt. So there is a salt particle, 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 and this water tries to goes up like that, it blocks. This part, yeah, from here water tries to goes back, this blocks. From here the water tries to goes back, it blocks. So not enough vapor there. So when there is not enough vapor, does it boil? No. You see that? If there is no a lot of vaporization, then what is vaporization? It's kind of the boiling. If vapor doesn't go up, it doesn't boil. And by that, it's just like this one. I am the salt, and then I block this door. I block this door. Like this. You see that? I am a salt and I block the door. Can you guys go out? No. So you cannot boil. Yes? But when it's a pure water, there is door is not blocked. It's open. Now you can easily go and boil. Go out is a boil. Everybody see that? Yes or no? Yeah. So if I am a salt and I block the door like this, and then you cannot go out. You see that? You cannot be boiled. We are the you are the water, I am the salt. I am blocking the door to go out. So you cannot. So no matter what happens here, you cannot go out. No matter how much heat I give, you cannot go in. Unless some really bad thing happens, maybe you can go out. Right? Everybody that? So I'm not blocking that. So that's like that. I'm here. Now you are a water molecule. Like you are a very pure water now. Now you can go easily and you can boil easily. Go out in boil. Everybody that? Yes or no? Yeah. So when you put the salt particle block the surface and water molecule cannot become vapor easily. So therefore we need to heat and long time heat and then only water molecule go up so we can boil. Everybody done? So it's all about the surface phenomena, blocking the surface. Yes? Like that. And then that M is just by measuring the temperature of the pure water, temperature of the boiling temperature of the water salt, and by knowing that value of Kb, you can easily calculate how much salt is there. Close equation means that. Everybody got that? So it's just like that. All right. So now I have one concept. So boiling point, um, uh, depression and freezing point depression. So we just talked that one. Now let's talk about the vapor pressure. What happened to the vapor pressure? So I am going to write here vapor pressure. So look here. So I am not looking the temperature now. I am looking the vapor pressure. Now let's talk about the vapor pressure. So I have the water here, pure water, water here. Now I close this one here, and I have a pressure gauge here. It shows the number. Everybody got that? Yes. So that shows the number. Now I have this salt water. There's a water here. So water, and I have a salt here. Water and salt here. Some salt is here. And I have this. I close this one, and I put a pressure gauge here. Which pressure gauge shows a bigger number? Pure water or salt water? What do you think? This is salt water. This is the pure water. Look here. So more water vapor from this liquid, more water goes here like that. And look here. So 1, 2, 3, 4, 5 go there. It might show 5. So here, if you count here, so maybe this guy is blocking this one. See that salt is blocking. Maybe only 2 goes there, so it shows 2. You see that? Pressure is like the counter of the particle. Yes? 1, 2, 3 counts. Yes? With the pressure, you can actually count how many particles are there. Everybody that? So which has a more vapor pressure? Is the pure water or the water with salt? Which is more?
Pure water.
Pure water has a more vapor pressure. Why is that? Because nobody is blocking this water molecule, so a lot of water molecule from liquid go to the vapor and give the pressure there. Yes? But here you see that water and salt. There are salt particles. So this is the water. This is a salt particle. So salt particles are blocking this water to go here. So less number of the vapor particle are there. Therefore the vapor pressure is low. Make sense? It's just like I go here, we cannot vaporize. So I stand here. I stand here. So outside is the whoever is out counting you. That's the vapor pressure. Can you go out now? No. Zero vapor pressure of this class. Now I open this one. Everybody go out. A lot of vapor pressure. You see that? Yes or no? Exactly. It's pretty simple, right? Yeah, but you are just looking this concept first time, so maybe you are feeling difficulty. Yeah? That is all about the blocking. Yes? Good? Alright, so that's that one. So vapor pressure is lower with the water salt, but pure water vapor pressure is higher. Yes? Now, we understand that. Now let's talk about the osmotic pressure and osmosis. So we still have a 5 more minutes. So osmosis. So probably you already know the osmosis in the biology if you have taken already biology. So let's look here. So this is a big tank. It's a tank here, and then you put a membrane here. A membrane that has a tiny hole. Tiny holes like that. You ever see that? Yes or no? Tiny hole. So if this is a membrane, this side I have water, pure water, and this side I have the water and blood cells. So this is water, and I have some blood cells. The blood cells. That red thing. Who is that? You see what I'm doing here, right? Yes? You look here. Now the water particle can go this side, this water particle can go this side, this water particle can go this side, this water particle can go this side. But do this blood cell can go other side or no? No, because they are too big. Yes? So can this guy go this side? No. This comes here, blocked by this guy. Yes? So this kind of the system is called the osmosis. You see that? From this side, a lot of water molecule can go. Other side, but from this side, small number of molecule can go this side. So this process is called what? Osmosis. Make sense? So where is the water, pure water side? A lot of water molecule go to the less water molecule side. You see that? So is there any student outside this room here? Nobody. Yes? Nobody. So we can go, so you are a water molecule, so you can go that side. So that's our osmosis. Make sense? And you imagine that this door is a semi-permeable membrane. Yes? So water from the more water side go to the less water side through the semi-permeable membrane. Yes? So this is called the osmosis. You know that? What do I mean by less water side? So there are some blood cells. So if there are blood cells here, definitely that side has a less water. That means. Make sense? So this side is a less water side, less water concentration side. Less water side. This is more water side. What do I mean by more side? More means all water here. In this side there is some water, some blood cells. You got that? So if you are separating the blood with the water, so let's say here, so let's say this is in this bag you have the blood. This is the water and the blood. Water and the blood. Now put in the water here. It's a pure water. It's pure water. So water from pure side go inside to the blood side. You got it? So that bag is a semi-permeable medium. Yes? Everybody that? So osmosis means water molecule from the more water molecule side go to the less water molecule side through the semi-permeable membrane. What do I mean by more? More means there is only water in one side. On the other side there is a water and blood both. Yes? So from pure water side, water go to the blood side. Blood also has water. Yes? Everybody that? So this phenomena is called the osmosis. Yes. Now I can do what I can do is now this is osmosis, but I can stop this osmosis. So what I can do is, so the water molecule trying to go from this to this side, right? Yes, from this to this side or this to this side. Water trying to go from this to this side, more water to less water side. Yes. So this is osmosis. But if I push this bag like this here, I apply some pressure, they can't come this way. So I press it here. And how much pressure I apply here, that to stop those water molecule to come other side, that is called osmotic pressure. Does that make sense? So let's look here. So this is semi-permeable membrane. We are going to try now out because there is a less water, we have more water here, right? And there is somebody pushing back this one. From outside, somebody is pushing back, meaning that he's pressuring this door. Can we go out? No, the door does not open. It's just like that. Every time that. So what you do is, so water are trying to more water. Look here, 1, 2, 3 are going this way, one is going this way. More water is trying to go this way. But if you want to stop this water coming this way, push this. So if you just hold this like this, or you push this way, this water don't come and they just block. So how much pressure you apply to block this water coming toward the blood side? That is called the osmotic pressure. Does that make sense? Yes, osmotic pressure is amount of pressure you apply to stop the flow of the water molecule. So how much time I have? So 4 more minutes. So now I just give 2 examples and we are done. So just read this, and if you don't understand, we can discuss in next class. Yes? Yeah, first we need to review. Now I have this one. Let's see here. So I have this one 100 gram water. 100 gram water. I have here 100 gram water. Same amount. I have here 100 gram water. 100 gram water. 100 gram, 100 gram, 100 gram water. And here I have 5 gram salt. Salt. Here 10 gram salt. Here 10 gram salt. Everybody see that? Yes or no? So look here. So in 100 gram water, 5 gram salt. In 100 gram water, 10 gram salt. So 10 gram salt is more, right? So this solution is called hypertonic. More. Hypertonic. This guy is hypertonic. Hypertonic. So this guy is called hypotonic. Small. This salt is small there. Yes? Hypo is big or hyper is big? Hypo is big. Hyper is big. Hypertension. Hypotension. Yes? Look here. There's a 10 grams, 5 grams salt, 10 grams salt, and the 10 grams salt. Now which are equal? Look here. This is 10 grams salt in 100 grams, 10 grams salt in 100 grams, right? So these are isotonic. Yes.
So then would a hypotonic solution also be an unsaturated solution and then a
I don't know that. I don't know about that. There are two. I'm just comparing two. For example, he got 90 in the exam. He also got 90 in exam. You both got 90, right? So you are isotonic. These are isotonic. Now, if he gets 60, he gets 80, then he is hypotonic. He is hypertonic. You see that?
What's the difference in the words? Hypo, hyper.
Hypo and hyper. You got that? Hyperactive student, meaning that he is very active. Yes? Hyperactive, meaning that more salt is there. Now, look here. So this is a hypertonic solution because that has 10 grams salt in 100 grams, and that has 5 grams salt in 100 grams. So this is hypotonic, this is hypertonic. But this is also 10 grams, this is also 10 grams in 100 grams. So this guy and this guy are isotonic, same. Everybody got that? So just read this chapter and see what happens. And we will discuss in next class. Yeah. If you don't understand, you can ask me. Yeah. Good. All right. So if anybody didn't do the attendance, please do it. So we are done 11 chapter. Now I have 12, 13, 14. So 14 I will not study for exam. So 12, 13. So we'll be studying. Yeah. All right.
The green bullet is didn't start this morning.
Alright.
I was at home, so I had to take the bus to go to school. Now I'm gonna go take the bus back and I'm trying to see if I can Yeah, I got games and stuff, so.
Okay.
All right. Yeah, you too.